Yeah. Can I just check the participants, how many are there?
Yes.
I just see you, so
Yes.
I'll start in around 2-3 minutes if nobody else comes. Okay. Uh,
Okay.
yeah.
I think someone because the last session will be on the Zoom. Oh, sorry, Meet. So some people can try to understand this new feature. That's why someone letting in.
So most of you use Meet, is it? And now it's Teams,
Yes.
so that's why.
Yes. Yes. Yes.
Oh, okay. Okay.
I
Ac-
think they are getting some time to manage it.
Okay. Do you know others who have
Hopefully.
joined this course? You know others?
Yes. 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 Yes.
Oh, okay. Okay.
We have
Okay.
lots of 10 to 20 student in the live session, my previous live session.
Okay. Okay. So where are you from?
Actually, I am from Bihar, Munger.
Okay. Acha. So I am a PhD student here in Indian Institute of Science, Bangalore.
Oh, nice.
Yeah. So I don't know. So can if you know people who are willing to join, can you just confirm if they will be joining, or else I
Yes,
I would get going.
yes, yes. And actually, I am preparing
Mhm.
for JS,
Okay.
and this course I have done already 2 year back in 2020. I have all notes on all lecture
Okay.
notes.
Okay.
So, and
So it's kind of a revision for you.
this is my revision. Yes.
Yeah. Okay. Okay. So I hope I have selected certain questions which I'll be discussing. So
Yes.
so let's see if it is helpful for you. Uh,
Yes.
Actually, it's for UG as well as PG. So some questions are pretty simple if you have already done these courses, but we have to cater to everyone. So I have some easy, simple questions as well. But
Yes.
I am confused. Should I start? Okay, I should start, in another 2-3 minutes because then we'll run late. Uh,
Yes. I will interact after the live session for what some student. I think
yeah. Yes. Yes.
actually, if some student can't be joined, then I will concern about it. Okay.
Yeah. Okay. Okay. So no, I just wanted to confirm if somebody else is joining. Otherwise, I'll start.
Okay.
Yeah. Okay. So let's start. Can you see my presentation, right?
Yes.
Okay. So your background is in physics only, right? Uh,
Yes.
so you have done your BSc?
Yes. I am pursuing MSc in Munger University.
Okay. 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 Fine. So I think you'll have the basic ideas already there. So I'll just get going. So, what I'll do in this 2-hour sessions each week is that depending on whatever is supposed to be taught in this week, I'll prepare some questions and their solutions. So we will discuss these questions and solutions, and along with that, I'll discuss some of the basic concepts which would be relevant to this problem solving. Okay.
Yes.
Okay. So, and then if you have any doubt, feel free to ask. Okay.
Yes. Yes.
Yeah, so this is already, I think, as you have done all the courses, so it's might be known to you, but just for the sake of introduction. So here, if you have a system, we can have mainly two kinds of description. We can have a microscopic description or we can have a macroscopic description. So if you have maybe a glass of water and then there are particles inside, what microscopic description means is that they there are molecules and they're moving and they're so what is their position, their momentum, and all this kind of description is the microscopic description, right? Hello?
Yes, yes.
Yeah. But then what is the macroscopic description is that if you measure the temperature or the pressure or the macro variables, right? So this is the macroscopic description. So we already know that thermodynamics is actually based on this macroscopic description of it describes phenomenologically the macroscopic systems. Okay. So
Okay, ma'am.
okay, so now I think is this concept clear to you, right? That several microstates can correspond to a single macro state. So this should here this one should be a macro state. One second. So this should be a macro state. So several microstates correspond to single macro state. This concept is already clear to you.
No, ma'am.
Okay, so that means that suppose if you have a glass of water and you are measuring the temperature. Okay, so
Yes.
So when you measure the temperature is a macro variable. Now you're measuring it maybe at a interval of like you have 5 glasses and you are measuring the temperature. Okay. And then in all of them, the temperatures are the same. Okay.
Yes. Yes.
But then that doesn't mean that each of all the molecules inside the glass in each of the 5 glasses are having the same configuration, right? They can have different momentum and different positions and they are continuously moving, right? So their positions and momentum of the individual molecules are continuously changing. But then when you measure the equilibrium temperature, that's a fixed value, correct?
Yes.
So that means that the macro state, which is defined by the temperature here, can correspond to a number of microstates, which can be defined by the position or the momentum of the particles. Okay.
Yes.
So
Yes.
these concepts lie at the heart of how what is thermodynamics and how it can be related to statistical mechanics and all of that. Okay, so it was just an
Yes.
introduction. Now talking about the laws of thermodynamics. So we know the
And
zeroth law.
the
Yeah,
one
yeah,
question is, ma'am. So
yes,
there is a single microstate can correspond to a single microstate. I think there is macrostate, isn't?
yeah. So
Uh,
this should be a macro state. Yeah, this one should be a
yes,
macro
yes.
state.
That's why I'm asking. So I am not clear here. That's
Yes,
okay.
yes, it should be a macro state.
Yes. Okay, ma'am.
Okay, so now let us go into the different laws of thermodynamics. So, what is the first law? It defines the temperature, right? So, it gives us a definition of the empirical temperature, and I won't go into the details of it because you already have the basic idea, right? If two systems are in
Yes.
equilibrium, like if A and B are in equilibrium and then B and C are in equilibrium, that means A and C are also in equilibrium. So, and from there we can have a description of this state function, the concept of the state function, which is the temperature, right? Okay. Now coming to the first law, and first law is basically the conservation of energy. So where it says that this Q means the heat, E is the internal energy, and W is the work done. And you already have the concepts of exact and non-exact differentials, right?
Yes, yes.
Yeah, okay. So Q and W are non-exact differentials because they have path dependence, while E or the internal energy is an exact differential and it's not dependent on the path, right? Okay.
Yes.
So now when you find the work, this work like for a system, like if you have pressure and if you are defining a system by pressure or volume, you know that work is defined by PdV, right? Like dW is equal to PdV, minus PdV to be specific, to take into consideration the one second. the
And
sign
it's depend on the work, I think, minus and plus.
minus and plus depends on whether work is done on the system or by the system. But then in general, we can have generalized displacement and forces. So suppose if you have a wire and if there's a tension, then and because of the tension, there's an increase in length, then we define the work done as FDL, right? So generalized forces are always intensive quantities, while displacement, generalized displacements are extensive quantities. So this concepts are already clear to you, right?
Yes.
Okay, so now let us see a very simple question. So it's like this is the equation of state that is given to you. So and this is the question that the F is defined, and we are changing the length of the substance from L naught to L naught by 3 quasi-statically and isothermally. So what would be the expression of work? So can you let me know?
Yes, we use FDL concept instead of PDV.
Yes,
Uh,
exactly. So, and then we have to integrate, right? We have to,
integrate. Yes.
so can you let me know what it will be? Like you you can just work it out, and then we'll see if it matches with our answer, right?
Okay, okay. It takes some time. Okay.
So we have another attendee here, Kishant. Hello, Kishant. Hi. So are you from physics background?
Am I audible, ma'am?
Hello.
Am I audible?
Yes, yes. So you're from physics background?
Yes, ma'am.
Okay, okay, fine, fine. So I think this is pretty simple. So I can just share the solution with you guys.
Uh,
Yeah,
It is just
yes, 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 yes.
yeah.
Okay.
So it would be
I
simple.
am using same procedure. Uh,
Same,
yes,
right? Yes, exactly.
yes.
So Kishant, it's clear to you? Both of you, it's
yes,
clear, right? Okay,
yeah,
fine,
obvious.
fine, fine. Very good. So
Ma'am,
yeah,
ma'am,
yes,
actually,
yes.
I have problem that in the assignment two, and the problem
Okay.
number 2, 3, 4, actually none of the options is correct. There is need of correction in the options. Assignment two.
Okay, actually, see, problem is that I am doing this TA-ship under PMRF, okay? And so I'm not supposed to discuss those questions in particular in these sessions because I think they said that we are not supposed to discuss those questions. So that's why I have been choosing some other questions and discussing that. So if you have any problem with the assignment that has been shared, you can maybe contact the instructor. Okay.
Yes, ma'am. Message him, but no
And
reply.
but even then, if it is so, if there's a confusion regarding any question, you can write to me or you can share the question here in the chat box. And later at the end, we can have a look at how this can be procedure or something. But I'm actually not supposed to discuss the assignment questions in particular. Okay. Uh, is that okay?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. So now let us look at the other concepts. So we know the concepts of, so now here you can have different, so there are different questions that can come regarding, so if you have maybe surface tension is specified and there's an increase in area and what is the work done and all of that. So all this is based on the similar kind of concept, right? So there can be several questions in this type. Okay, so all this follows the same concept. Now, let us look at some other and another concept, which is of the concept of response functions. So, what do you mean by response function? Is that so? Suppose if you provide heat to a system, how does it respond? So there would be increase in temperature, right? So how much heat results in how much increase in temperature? So this is kind of a response. Or if you apply pressure, how does the volume change? What is the compressibility or what is the expansivity? So these are how the systems respond to whatever we are doing. So these are how the basic response functions are defined. Cv is the specific heat at constant volume, it's in constant pressure, it's Cp. And then this is how compressibility, isothermal compressibility of gas is defined, and this is how the expansivity of gas is defined, right? So in different questions, you can have, you might be asked to solve this kind of quantities. So you should have an idea about how these are defined, okay? Hi. Hi. Hello.
Yes, yes, ma'am.
Yeah, okay. I'm just confirming that you all are there. Okay.
Oh,
So
okay.
okay, so and then one another interesting important thing, or because these questions are quite common, right? If you have a adiabatic system, how these things depend on each other. So this can come in different questions. So if you look at the assignments, there I think there are questions which are based on this kind of dependence. If you have the initial pressure and volume specified, how would the final volume and pressure be if you have a adiabatic process going on? So all these are based on this kind of equations, which so these are polytropic processes, and you can you should have an idea about this formulas. Okay, so now
Oh,
this is a second question. So here we already know. I think most of us know about this, right? This is a Carnot cycle diagram, right? So now here,
Yes.
which processes are adiabatic and which are isothermal? Uh, can you write in the chat box maybe?
Yes, ma'am.
C and D, I think.
And B and DA are the adiabatic.
C
B, B,
and
B,
D to
Conversation
A.
we can
ex 1 second. BC and DA are the adiabatic processes, right? And AB
Yes.
and CD are the isothermal processes. So, so this is what we already know, and that's why we can just look at it and say, right? But then, how do we, if we have a normal, like maybe we have a just two graphs, one is an isothermal process and one is a adiabatic process. How do we differentiate between them? So this can
from the
come in
curvature,
yeah,
from the slope.
from the slope,
Slope.
right? Exactly. So it's like so if you start with this, you can find dp dv, and there you'll see that adiabatic adiabats are always steeper than the isotherms, right? So this there are in generally in competitive exams we quite often get this kind of questions where we have to identify what kind of processes are going on, and there are graphs given, right? So these concepts can be helpful there. Okay. Okay. So now there's another question. So the internal energy is given to you, okay? And you have to find the heat capacity CV and CP. So can you tell me how to proceed with this? Maybe you can write in the chat box, or you can.
For the specific heat, CB del U upon del T at constant B and del U upon del T at constant P for CP.
Okay, but so here in the expression of U, you have T and V. So del U del T at constant V, that's fine. But how do you find CP then?
I will use Mayer's equation Cp minus Cv equal to R.
Okay,
But
that
for
Because
molar one,
so Cp minus Cv equal to R is for an ideal gas, right? Here the
sorry.
gas
Yes.
satisfies van der Waals equation. So if you
ma'am,
use the same, yes, yes, yes,
from the wonder what we will get V in terms of T, and then we will put
yeah,
in terms of,
okay,
then we will make an integration. Sorry, differentiation.
yeah, okay, yeah, right. So can you just maybe do the CV and let me know what would be CV from here? CV is pretty simple, right? Just look at the expression for U and let me know what is CV.
See, see,
Minus A minus A C minus sorry.
from C.
Yes,
C.
yeah, it's C, right? And then how do you find Cp? So let us look at the solution. Okay, it would be easier for you to relate. I think you are going in the correct direction only. So so you start with this. So Cp means dq dt at constant pressure, and dq you can write it as du plus pdv, right? Now
Yes.
you can also expand it in this format, right? So du dt v plus du dv at constant temperature plus p into dv dt. This
Yes.
comes
Yes.
directly from dq dt. So now here, when you have the expression where u is written in terms of t and v. So you can find dv here and you can replace it here, right? Is this clear till here?
Yes.
Yes, ma'am.
Okay. Yes. And then now you'll use the van der Waals equation to find dv dt, right? So this is your van der Waals equation, and you use dv dt to, like, you use the van der Waals equation to find the expression for dv dt, and you replace it here, right? And that's how you get Cp. So that means that if you are given a state of equation, and if you are given this kind of questions where your internal energy is being specified and you want to find Cp, Cv, or the other response functions, you have to use the this state of equation, the state of equation. You cannot just sorry, equation of the state. You cannot generalize it like so. This is a very general problem that we often make. Very general mistake that we use Cp minus Cv equal to R, but that's not always true. So you have to keep these things in mind. Okay.
Okay, ma'am.
Yes.
Ma'am,
Okay.
P minus CB equal to R, this is valid for an ideal gas.
Exactly, yes. So you have to keep in mind what is the equation of state that is specified. Like what is the system and what equation of state it satisfies. So if it is said as in ideal gas, then you can use that. Otherwise, you should not use that. So you should keep that in mind, because we all have done these mistakes and we should be careful about it. Otherwise, our answers will be wrong. Okay. Okay, now,
Yes, ma'am.
yes. Now let us come to the second law of thermodynamics. So, what does the second law tell us? So, it tells us that for so there can't be any process where we just get complete conversion of heat to work. Like there has to be, so there cannot be complete conversion. So if you take some heat from a source and then some amount of it will be converted to work, and some will be uh, given to the sink, which is given as QC here, as you can see, right? So efficiency is never one; it's always less than one. So that explains that we can't have perpetual motion machine of second kind. So this is clear to all of us, right?
Yes, ma'am.
Yeah, and then from the second law, it gives us an idea about the direction of flow of heat. So if you look at the Clausius statement, it tells us that heat transfer always takes from the transfer of heat is always from the hotter to the colder body. So that gives us idea about the natural direction of flow of heat. Now, what's interesting here is that from the use of second law of thermodynamics, we can define the maximum efficiency that one can obtain from a cyclic process, and that is when the system is reversible, right? And so that is what is a Carnot engine, right? The efficiency of a Carnot engine is the maximum. All these concepts are already, I think, discussed in class, and you all might have idea about it, right? Okay, so I would go to the next section. And then it's important that here we have got this concept of entropy that we have obtained from the second law. Like from the first law, we get the concept of a state function, which is the so what is the state function that we get from the first law?
Internal energy.
Yes, internal
You.
energy. Yes. And what is the one that we get from the zeroth law?
Uh,
Temperature.
Temperature. Right. And then what we get from the second law is entropy. So,
Entropy. Okay.
yes, right. And then, so this is a very important concept which defines almost all uh, processes in equilibrium is that the entropy of an isolated system always tends to maximize as it approaches the equilibrium. Okay. So now let us see how we can use this concept in solving some of the problems. Okay. So question 4. So here we know that this is how the Carnot cycle looks for an ideal gas. Okay. Now can you tell me how the TS diagram, TP diagram or TV or UV diagram look like? So let us take one at a moment. TS diagram. So how will that be?
Ma'am, for the diagram for the BC and DA, there will be S is constant. So if we make T in the Y and S in the just direction, so it will be
Something like a rectangular structure, right?
Yes. Yes.
So it should be something like this.
Yes.
Okay. Uh, and then what happens if we do a TP diagram? So you can just try doing it, and then I'll share the solution with you, right? Because otherwise it's difficult for you to explain as well. But is that okay?
yes, ma'am.
Yeah. So could you make the TP diagram, both of you?
Yes, ma'am. Wait a second.
Just use the concept that where it's expansion and where it's compression. And if the volume increases, then what happens to the pressure?
We will draw on four diagram for Carnot cycle.
Yes, so we generally do this PV diagram, right? But now let us
Yes.
see how it looks at in other scales. Like in TS diagram, it looks something like this. But then you
Yes.
can try in TP diagram, and once you are done, you can let me know. I'll share my solution and we'll see if it matches. Okay.
Okay. I think we use Maxwell relation for this.
You don't have to actually just
Uh,
so you can use, but then it would be a very lengthy process. But what we can just simply do is that, so if you look at here, what is happening here?
isotherm.
It's a isotherm, but so the processes is increase in volume, right? So it's a expansion process.
Yes.
But now you have, so it's a isotherm. So first line should be like this, as the same as this, right? Because it's in constant temperature. But now what happens to the second part where the temperature is not fixed? So here it's again an expansion, correct?
Yes.
So if it is an expansion, that means the volume is increasing. So what is happening to the pressure? So the pressure should be
Decreasing.
okay. So the slope should it should be towards this side, right? So that the pressure decreases.
Yes, ma'am.
Okay, so
So
let me share the solution and then explain to you. I think that will be easier. So you see, this is it's an isotherm, so it's a straight line. Now the pressure is decreasing because the volume is increasing. So you have a slope like this.
yes, ma'am.
And then again it's isotherm. And then again, now there is a compression. So the pressure is supposed to increase. So you have a slope like this. Is this clear?
Yes.
Yes, ma'am.
Okay. Okay. Now what happens if you do a TV diagram? That should be pretty simple, right?
Okay, ma'am. Picture will be same, ma'am. Graph will be same.
Same as so it should not be same because first of all, here you have, so this is pressure. Now you have volume here.
Yes.
So
Yes.
so you have to change accordingly. So in this place, what was happening? The pressure was decreasing. So what will happen to the volume? The volume will increase, right? Hello? Did I lose you? Hello?
Yes, yes, ma'am.
Yeah. Okay.
Okay, ma'am, pressure is increasing, then volume is decreasing now.
Here what is happening? Here pressure is decreasing, right?
Decreasing. Yes.
So volume should increase. So see, here
Yes.
you have the volume here. So the volume should have something similar to this thing because volume is increasing,
Yes.
right? So the only difference is that this was with P. Now we have along with the y-axis is T. So you have something like this here. So this is an isotherm. So the temperature, it's a straight line, but then the volume increases. Obviously, the slopes of this and this would be different, but you can see this thing, right? Like it will all increase because it's an expansion. And then this is compression. So it will decrease. Is this clear to you?
Yes. Yes, ma'am.
Yeah, okay. And now what
And I
happens
think
when you,
UV is same as PV. Sorry,
yes,
T. Yes.
yes. Why?
Because
Because,
actually internal energy depends on temperature only.
yes, exactly, exactly.
So
So
I use
there's
this
a,
concept.
yes. So this is how you can write all the different kinds of diagrams for the Carnot cycle. This is clear to you, right?
Yes.
Yeah, okay, fine. So now question 5. So you have this entropy S versus internal energy graph. Okay. And then you have this like three phases A, B, and C, and the temperature of each phase is TA, TB, and TC. So what should be the inequality that they should satisfy? So can you tell me what is the concept that we'll be using here?
Area under curve.
Uh, no. Uh, so just think of how temperature is related to S and E.
Okay. We have a question. DS. I think DQ equal to TDS.
Yes, dq equal to TDS. Okay. Okay.
And DE like internal energy.
D, D is internal energy. Yes.
Yeah. So we use first law of thermodynamics here.
Hmm. Yes.
DQ equal to DE minus PdV. Okay.
Hmm. Yes.
So, for the
So,
entropy also. And
so,
we
so,
use DQ TDS instead of D cut Q. Okay.
yes.
So
Yes.
TDS equal to DE minus PdV.
Okay. So,
Uh,
what is ds by de? So you can just use
uh,
the partial differential, not partial differential, like the differential concept. So
yes.
TD, TDS is equal to DE plus minus PDV. So that means DS will be, so what would be the coefficient in front of DE in the expression for DS?
Uh, so DE equal to TDS plus PdV.
Okay, yes. So you have to
And
find DS by DE. What is
okay, okay. So
DSD?
yes, yes. DS upon DE equal to 1 minus PdV. So 1 upon T.
1 upon
So
T.
at constant volume, if we take the at constant volume.
No, we don't have to take in constant volume. We can
Oh,
just so suppose if you, so let me share the solution and discuss. Okay. So so suppose so this is how the thing will go. So if you write the expression, maybe 1 second. So let me share the, I'll just describe from here. So you have this, right? Now if you do DEDS, DEDS will be T, irrespective
yes.
irrespective of what is this value, we don't care because we can write always write DE as del S del E del S del one second, del E del S into ds plus this terms. So del E
Yes.
del S turns out to be T. So del S del E turns out to be 1 by T. It's clear, right?
Yes.
Okay, so that means here if we look at this, the
Yes.
slope,
Yes. So,
yeah,
yes.
this,
ds upon de upon ds equal to 1 upon t is actually I have derived. So
yes.
from
So that means the slope will give us the value of uh, the temperature, right?
yes.
So from here we can get the inequality as this is matching with your answer, right? Because
Yes.
yeah, so this has the slope is smallest here, so the temperature is maximum here, correct?
Say again, ma'am.
So the slope ds by de is minimum here at in B. So that means the temperature is maximum here because ds
Yes.
by
Yes.
de slope
Because
is equal to
inverse
1
of
by
the
t.
temperature.
Yes, exactly.
Yes.
Yeah. Okay. Okay. So now, yeah. Okay. So now let us go to the other question. So question 6. So here, this is your internal energy which is given, and you have to find the entropy as a function of temperature. So using the similar concept, the concept that we were doing previously, can you just try to solve it out? Just use the same concept.
Yes. So the entropy S T is a function of the internal energy of the temperature. So we use integrate with respect to T, I think,
Yes,
for D,
yes,
ds upon
yes.
dt. Yes. So it is ATQ upon 3 plus BT per power 5 upon 5. Okay. So something is, I think I am wrong.
Yeah, your concept was correct, but then I don't know. I think you just got confused in something. So,
Okay.
so the answer is
I
C. Okay.
yes. T. So
So we have Anushka here. There's another. Yeah. Hi, Anushka.
Hello, ma'am.
Yeah. Hi. Hello. So, you have you are from physics background, like you can understand what I'm telling right now, right?
Yes,
Yeah. Okay. Okay. So, just if you have any doubt, just let me know. Okay.
yes, sure, ma'am.
Yeah. Okay. So just try to work it out in the way that your internal energy is given. So I think Abhiram, can you just mute yourself? I think there's too much of sound. Yeah. Okay. So how do you proceed is that see if you use this here, we know that dq equal to dE plus PdV. So from here we write dE, which is the internal energy, as TdS minus PdV. Now it's in fixed volumes, that means dV is 0. So from here we get dE equal to TdS. Now ds is 1 by T dE. So it's the same equation that we were doing in the last question. Okay. Now here the internal energy is already given to us. So what we find is dE from here. So we do this differential, and then what is ds? We divide this thing by T and we integrate to find the entropy. Is this clear?
yes, ma'am.
Okay. So in this way, you can like if you expressions like internal energy or other state functions are given to you, you can use the first law or the other or the concept of how the different potentials are defined, and accordingly find the state variables from there. Okay. So there'll be some questions later as well, which will use the similar kind of concept. Okay. Now question 7. So so here we have a gas which expands adiabatically from volume V1 to V2 by a quasi-static reversible process. And in this process, it cools from T1 to T2. So this is a reversible process. And now it's said that the same process is then again carried out adiabatically, but now irreversibly. And there the final temperature is T2 prime. So how is T2 prime different from T2? So can anyone tell me which concept are we supposed to use here to solve this question?
We use graph, ma'am. So for PV diagram, from PV diagram,
From PV diagram, how do you tend to do it?
just it is two adiabate from
So,
B1 to B2. Yes.
so both of them are adiabatic processes, but one is a
Yes.
reversible process and one is a irreversible process.
I'm getting some confused.
Just think how reversible and irreversible processes are different. So if you have an adiabatic process which is happening reversibly, and if you have a process which is happening irreversibly, what is the difference? Like if you look at the postulates that we gather from the second law, just try to recollect, or maybe
I totally forgot.
I'll give you a hint. So efficiency of reversible process is maximum. That is what we get from the Carnot's theorem.
Okay, ds upon t closed integral greater than equal to 0
ds
from this. Clausius inequality for this.
Yeah, that is true. Uh, so always in a reversible case, the entropy will be equal to dq by t, and otherwise we'll have the inequality as entropy always greater than expression, right? Dq by t. So that is there. But then, so how do you define efficiency from there? Think of
Uh,
think of a basic process. If you
okay,
have
okay,
uh,
ma'am. So
yes.
there is two theoremic. One is refrigerator and one is Carnot. So from we derive Carnot efficiency theorem
Yes, so
for
you
this.
have a Carnot engine. Okay, you have a
Yeah.
Carnot engine, and then so you have a source and a sink, and it takes heat. Maybe so the source is at T1 and the sink is at T2. Okay, and then you take
Yes.
heat QH and you give out heat as QC, and the work done is W, and then you define efficiency as W by QH, right? And so
Yes.
from there the expression is 1 minus T2 by
Oh, T2
T1,
upon
right?
T or T1. Yes. So and we also use it Q upon T1. So for work done upon in input energy.
Yes, yes.
So
If
we
you
can
want to
use the
just,
work instead of B2 minus B1. Like
yeah, so let me share this thing with you and see if it makes sense. Okay. So the answer is B. And let us see how. Okay. So if you define the efficiency for,
oh sorry.
yeah, so if you define the efficiency for a irreversible process, this will be given as 1 minus T2 prime by T1, right? And if it is for a reversible process, it will be 1 minus T2 by T1. Is this
Mm.
correct? Is this making sense?
Yes. Actually, I am making very complex for.
Yeah,
I,
exactly.
I am using this concept. Suppose we have
Using
a
here,
system like first is reversible, and then the getting input, then connect be irreversible. So it is indeed it is, but I am thinking in complex way.
yes, yes, exactly. So in this kind of things, the difference that we have to always keep in mind is that efficiency of reversible process is always maximum. So if you use this inequality that eta prime is always less than eta, you can get
Mm.
this inequality here. Okay.
Okay.
Yeah. Okay. Uh, Anushka, is it clear to you?
Yes, ma'am.
Yeah, okay, fine. Okay. So now let us look at the other parts of our today's session. So here we already have the idea of the different thermodynamic potentials, right? So when do we work with enthalpy, or when do we work with the Helmholtz free energy, or when do we work with the Gibbs free energy? So is this concepts clear to you?
Yes.
Okay, so
Yes.
yeah, we need to keep track of this equations, right? So here J is the generalized force and X is the generalized displacement. So that means if we have a hydrostatic system, this should be like H equal to E plus PV, correct?
It is in therapy. Yes.
Yes. So like this is a very general expression where we have J and X. And so J is the generalized force and X is the generalized displacement. But according to the system, we have to put the variables here. Same goes here. Okay. And then using these equations, we can do the differentials and finally get to this Maxwell's relations, which lie at the heart of thermodynamics. So all the stability expressions or understanding how systems are supposed to proceed or reach towards equilibrium can be described from the Maxwell's relations that we see here. So this is something which I just found it from Wikipedia, and I found it quite interesting in the sense that this in a way summarizes how one can use the Maxwell's relations. So suppose if you have this expression, what you can do is this expression can be written as a product of two terms. So del P del V can be written as at constant entropy can be written as a product of two terms, del P del S and then del S del V. And then what you can do is you can use Maxwell's relations to, so del P del S. So if you look at del P del S minus of del P del S, you can use the Maxwell's relations to write it as del T del V. And then again break it to two and then use it for other expressions. So if you are so if you just look at this expressions, you'll see how, so these things are very useful in solving equations where suppose you have one term given and you want to find, so if you have been given this term and you want to find something like the compressibility or something, then you can use this kind of equations, and this is how we should be proceeding with it. So you can try practicing all this kind of conversions because that will help in problem solving. Okay, so now let us look at another question. So this is question 8. So here what we see is, so this is our thermodynamic function. Okay, so where G is given to us. Now, which one of the following relations are true? So can you try solving this? So the hint that we will be using is that you have the expression for G. Try to write it in terms of differentials. Try to differentiate it and write and see which terms remain. And then can you let me know the answer? We have time actually. So try solving.
Okay, ma'am. I can solve it.
Yeah. Okay. Anushka, can you try solving it?
Yes, ma'am, I'm trying.
Yeah. Okay.
The answer is A, ma'am.
Yeah, so how do you do it?
I use just Maxwell potential. To use, just use the above uh,
Expression.
equation.
Yeah.
Yes.
So how do we do it
Actually,
is uh,
yes, yes. Actually, we have a shortcut key for to derive Maxwell potential. I use this.
yes. You use that trick how we are supposed to remember it? That
Yes.
SPTV thing? Okay, okay. Okay. So here so this is a simple example, but then so you can have different other potentials, okay? Maybe the free energy or something like that, okay? Or else maybe if you are given the Gibbs free energy and you find the S and the V, and then in some question you can be asked to find the equation of state. So
Yes.
once you find these expressions, you can use them to find the equation of states, okay? uh, okay, now let us look at another question. Uh, so this is the free energy, okay? This is Helmholtz free energy that is given.
Okay.
Yeah, and then we have to find the internal energy from here. So can you try solving it? It's another.
Actually, I
Hmm.
know, ma'am. Recently, I have solved in the assignment.
Oh, is this in the assignment? Okay.
Yes, yes.
Oh,
No, no,
okay.
no. This is not in the NPTEL assignment. We have.
Okay, some other assignment. Okay.
Yes, yes, yes.
Okay, so we'll wait for some time for Anushka to solve it and then we'll see if it matches, okay?
Yes.
Ma'am, can you please explain the solution? I'm not sure how to solve it.
Okay. So here, so for this case, we have the Helmholtz free energy. Okay. So what is the expression for Helmholtz free energy? It's given as U minus Ts. So U is the internal energy and T is the temperature, S is the entropy. Okay. And then the internal energy is again, so you can write internal energy in terms of the free energy, which is written as F plus Ts. So we need to find the internal energy and F is given to us. So what we have to do is we have to find the expression for T and S, right? So what we do here is we use this differential form. So df. So do you have idea how we are getting to this form? Df is equal to minus s td minus pdv.
Yes, ma'am.
Okay. So that means del f del t at constant volume is given as minus of s minus entropy, right? So if you are given the expression for f, you can find the expression for the entropy. Correct?
Yes, ma'am.
Yes, ma'am.
Yeah, so this is your expression for f, and then so here it's like this is a constant term, so it's being taken out. And then what they have done is they have found the differential del f del t at constant volume. This is what is present here, right? So what you do is you find the expression for that. So you can see here it all has constants and then the temperature that is there. There's no other term, all constants and temperature. And then so here this is the expression for u. You have again temperature and you already know the expression for f. So you put this expression here, and if you try solving, you'll see that you'll get an expression like this.
Ma'am, I have a doubt.
Yes.
That in that equation, U is equal to F minus T of delta F by delta T at constant V. Uh, we are we are assuming that the V is constant, right?
Hmm.
But in the given equation in the problem, they have not mentioned that V or T are constant. So we just assume that.
Okay, so see, it's like this is your differential expression. So if you write df, So how do you normally write df in terms of T and V? You write it as df is equal to del F del T at constant volume into dt, right? So this is just like solving the partial differentials. So if you have to, you have F, which is function of T and V, right? Hello? And,
Yes, ma'am.
so see, this is just, if you just try writing F is a function of T and V, and now you are differentiating it. So you'll write in terms of a differential, so you'll write df. So how will you write it in general? Don't look at these things, just write it in general. So what will be df? Df will be del F del T at constant volume into dt plus del F del V at constant temperature into dV. Is this correct?
Yes, ma'am.
Okay. So then now this is the equation that you have. You have written something and this is what we have. So now if you compare, this is what you get, correct?
Okay, okay, okay. Yes, ma'am. Now, yeah.
Yeah, so this is always true. So this is an expression that you are getting. So the rate of change of free energy with respect to temperature. So if the dependence of free energy on temperature at constant volume has a dependence like this. So that gives us a value of entropy. But that is always true. That does not depend on whether our system is in a constant volume or not. This equation is always true. Okay.
Yes, ma'am. Okay, got it.
Yeah. Okay. Okay. So similarly here, like here we have this Helmholtz free energy. We can also have Gibbs free energy, and like in the last question. So even in the last question, if you look at, you got something like this. So here when you write del G del T at constant n and p, and then del G del P at constant n and t, these equations are always valid. It is not dependent on what your system or what the particular system is doing at that moment. Okay.
Okay, ma'am.
Yeah, okay. So now this is another question. So this is the expression for S that is given to us. So we have entropy and we want to find the Gibbs potential. So how do we proceed with this? Just look at this expression here. So you want to find this and you have what is S. So you know what is S, and S is written in terms of U and V. And then you have U here. So what do you have to do? So if you have a question like this, how do you plan to proceed?
Uh, we have to eliminate the T and P. That is,
Hmm.
to make the equation only in terms of U and V. So we'll have to express T and P in terms of U and V as well.
Exactly. So how do you do it? So you have S. Now you want T and P. So just try to use the first law. So what is the expression for the first law?
The dq equal to du minus pdv. Actually, I'm working on it.
Okay, okay. So what about others? So Anushka, try to write the expression for, so if you use the first law, what do you write? We write as dq equal to du plus pdv, right?
Yeah, ma'am. I'm trying.
Yes, and then try to write dq as tds. Okay, we have someone else, Jamuna. Okay, so Jamuna, you are from physics background.
Yes, ma'am.
Okay, okay. So you can understand what we are trying to do here, right?
Now only I join.
Yes.
Now only I
So
see that.
yeah, so the question is that your entropy is given and you have
Okay.
to find the Gibbs potential.
Okay, ma'am.
So okay, I'll give you some more time. Any luck, guys? Okay, can anyone just say how you are trying to proceed with it? And let us see if the process is correct at first.
Uh, we have expression for s, so we can get ds from that,
Hmm.
which then comes in terms of u, v, and constant.
So you have expression for S. So are you trying to do it like you're considering S as a function of U and V and trying to proceed?
Yes.
But so how do you plan to express temperature from there?
Well, uh, what I did was we had dq as du plus pdv, so then tds becomes equal to du plus pdv. So
Hmm.
t becomes equal to du by ds plus p dv by ds. Uh, so
So
uh,
try to write it like so. The first two equations were okay, and then what you do is so del S del U. What is del S del U?
um,
Is it 1 by T? Check from the equation. So
Ma'am,
you
it is only dc equal to minus sgt plus bdp we are getting for this.
no, no, see, we already know the dependence of S on internal energy, right? We did one question where we had this slope, the concept of slope coming in. So what do we write? We wrote del S del E as 1 by T.
right.
Do do you remember that? Yeah. So how do we get that? So maybe if I just go back, I'll just show you from here. I don't want to show you the exact solution at the very first. So you have
The e which we had taken was that was a u in that question, right?
yes, yes, yes. So E and U, these are all internal energies. Okay. So
Uh-huh.
yeah, so if you write here we want to, so here what we have is, see this equation and think E is U here. So du is equal to TdS, and then it should be minus PdV, correct?
Yes, yes, ma'am.
Yes. So then just try to write in terms of S. So what is TdS? TdS is du plus PdV, correct?
If we use right side in plus, then D equal to minus PdB for TDS.
DE is equal to TdS minus PdV.
Oh, then TDS equal to DE plus PdV.
Yes. And now if you divide it by T, what do you get? DS equal to, we get something
D
like,
DE
yeah,
upon T plus PdV. PdV upon P by T, PdB
yes,
upon T. Na?
yes, exactly. So now what does that mean? If you write DS in terms of del S del E into DE plus del S del V into DV and then compare, what do you get? You're following, right, what I'm saying?
1 upon T. Yes, yes, yes.
Yes. What about others? Others are following?
So
Yes,
del S
ma'am.
upon del S upon del E equal to 1 upon T plus P upon T into del B upon del E.
Wait. Uh, we don't do it that way, okay? So del S, just write this equation first, that ds. So I think I have to find a way of writing here, otherwise it's,
Yes, yes. Del S upon del E equal to 1 upon T. Uh,
yeah, but the expression that you are saying, so there is a confusion there, right? So when you write del S upon del E, we don't have the extra PdV term there. So it's like
okay.
you write ds. So just try to write whatever I'm saying at first, okay? So ds is equal to del S del E into dE plus del S del V into dV. Is this correct? Like understandable for everyone?
Yes. Okay, I got
Yeah.
it.
Yes. Now,
S is the function of P and B.
yes, and then compare it with the expression that you have. So Anushka, it's quite similar to what we were trying to do here, right? Here, when we were trying to compare in this question, we did the similar thing,
Right.
right? So what we do here is we we write it in terms of the differential and then compare. So similarly, try to write S in terms of the internal energy and the volume, and try to write how the differentials look. So what is del S by del E and what is del S by del V? I have found a way of writing. So we write it as ds is equal to, it's very difficult for me to write. Del, maybe U, I'll write it as U at constant volume plus Sorry. Excuse
There
my
is
bad
du
handwriting.
in multiplication. There is du, man. Uh,
In
in
multiplication?
first term. In first term, del s upon del u into
Yeah.
du.
Yes, correct, correct. Thanks. I'm struggling to write, so I'm doing all mistakes. I'm just trying to make it understandable. Somehow I have to find a way of writing. Okay, so this is dv. Okay, this is at constant u. Now, the expression that you have is you have ds is equal to 1 by t into du. Correct? This is this term correct?
Yes, ma'am.
And then you have plus p dv by t because you have divided by t. Now compare these two. So del S del U at constant volume is equal to 1 by T, and then del S del V at constant internal energy is P by T. Correct? Uh, is this making sense? Hi. Hello, guys. I'm at the
Yes,
fear.
ma'am.
Yeah, I'm at the fear of losing you guys, so that's why. Okay, so so you have understood till this, right? Everyone?
Yes, ma'am.
All others? What about others? Everybody is quiet. We have some new people coming in now. Uh, Anushka, Jamuna, Ayub, Yazini, everybody is clear?
Yes, ma'am.
Okay. So what do we do now is we have S. So we will do this differentials, right? We have S. We will do this differentials and we will find the expression for T and P. Correct?
So, ma'am, from the given equation, we can derive 1 upon t, na? Where is s equal to c into u upon 3 from this?
Yes.
Yes, yes, ma'am.
Yes. From here, try to do del S del U. So if
Yes,
you do
yes.
del S,
Just wait, ma'am.
yes. Yes. Okay.
So it is 3 upon 4 into c upon b per power 1 upon 4 into u per power 1 upon 3.
E to
It
the
is
power
del
1
s
up.
upon yes 3 by 4 minus 1
It's is 1 by is minus 1 by
so minus 1 upon 3, so I just put
1
down
upon 4.
the 1, sorry, yes, 1 upon 4,
Yeah.
my mistake.
Yes. Yes.
So it is 1 upon t equal to 3 3 by 4 into c upon b to the power 1 upon 4 into u to the power 1 upon 4.
Yes. And then
So
similarly, you have to find P.
okay, ma'am. Okay, give me time.
Others are trying and others can do.
Yes, ma'am.
Yeah, okay.
Yes,
So
ma'am.
just we use the del s upon del v, we get the p, we get the answer p upon t, the same like.
Yes, yes, yes.
So it is c u t to power 3 by 4
C into u to the power 3 by
into
4, 1 by
1
power 1 by 4, v to the power minus 1 by 2.
yes 1.
And then you have to again, so you have to find P. So what you do is you multiply by T, like multiply by the expression
Actually,
for T to,
ma'am,
hmm,
b to the power minus 3 by 4, isn't?
B to the power minus 3 by 4. Yes,
Yes. So
it's
it is
normal
equal to
differential.
p upon t.
That is equal to P by T. Yes, and then you have to
Yes.
find P. So you already know the expression for T. So just multiply it by T. So you get the expression for just P. Correct?
Yes.
And
Sorry,
then,
ma'am, once again, please.
yes, yes. Where do you have doubt?
Yes, ma'am, we find dou s by dou u and dou s by dou v. Then how can we find p
So,
by
so
t?
yes, okay. So compare these two. So del S by del U at constant V is equal to 1 by T, and del S del V at constant U is equal to P by T. Is this clear to you?
Yes, ma'am.
Yeah.
So we
So
find know the value of 1 by t. Huh?
yes, we know the value of 1 by T from del S del U, and then we
Yes.
also find the value of P by T from del S del V, and from there
Oh,
we find the value of P.
okay, okay.
So we have a p and 1 upon t.
We have P and 1 upon T, that means we have T. Correct?
Yes.
Yes. Now try to put it in the expression for G.
U minus t s. Okay.
Others can also try the same. Once you find the expression for T and P, try to put it in the expression. Because others we have U, we have S, and we have V. So you write T and P in terms of U and V and put it in this expression to see what do we get. If you are stuck anywhere, let me know, okay?
Okay. So just
Yamuna, can you understand now? Yamuna, Anushka, and Ayub, are you guys trying?
Yes, ma'am. So
Yeah, okay, okay. I try sharing the solution.
ma'am, just 2 minutes.
Okay, okay. I, if you're facing any problem regarding any step, just let me know, okay?
Um,
Yes.
ma'am, my answer is not matching any of the options.
Okay. Uh, okay. So should I share the solution?
Ma'am, I think we should not have converted the T and P in terms of U and V,
Okay.
because in first option they are kept T and P, and in fourth they are kept the S and the S.
But then you
If
have to, in
if we
that
convert
case, huh, yes,
the
yes, tell me.
final answer in terms of U and V for G comes out as minus U by 3 plus 1 by 3 of U into V raised to 1 by 2.
Okay, I think there might be some mistake, maybe some calculation mistake somewhere. See, the process is like that because you have to bring all of this into some common terms, right? Only then you can get a simplified expression. So, excuse me. So here you have U and V already there, and S is also there. So in this expression, you have U and V. So it's the easiest thing that you can try in bringing all of this to the same term is to work with T and P. So I guess there might be some, some slight mistakes in the calculation. So what I'll do is I'll share the solution and let us see where we have gone wrong. Okay.
Okay, ma'am.
Yeah. So the answer is C, which is 0. So I'll erase this thing. Okay, let me just, yeah. So the answer is C. And let's see how we get to that. So does your expression for T and P match? Just check the expressions that all of you have got and then see when you put it here, does it come out to be 0?
Ma'am, my expression for T is correct, but P is wrong.
Okay, so I guess there might be a slight mistake maybe,
Yes.
because I guess this is correct, right? U to the power 4 by, just let me see. So you find the expression for P by T and then multiply by the expression for T. Did you do that?
Yes, ma'am.
No, I made mistake.
Yeah. Did you find the mistake?
Yeah, myself also
Yes,
I
ma'am.
didn't consider a T.
Yeah.
I didn't multiply the T value.
Oh, okay. So see, because what you get out of del S del V is is P by T. But then you have to find this term here, right? You also have to find the expression for P, just P, not P by T. So you have to multiply by that term. So is this making sense? Like there might be some calculation mistakes in what, like, you are trying to solve it and in some steps there might be some mistake, but is the concepts understandable to all of you?
Yes, ma'am.
Yes, ma'am.
Yeah. So whenever you get this kind of expression, you have to see that. So it's written in terms of U and V. So it's easier to convert the terms which are not in terms of U and V to something to these terms, so that it's easier to bring all of them to the same terms, and you can do all cancellation and everything, and then find a simplified expression. So this is a normal, like the general process of working out this kind of questions. Okay, so maybe I'll go to the next question. So is this okay for everyone?
Yes, ma'am.
Yeah, okay. So this is the next question. So you have this thermodynamic system where U is specified, U is given as P into V, and then P is also specified, where P is a constant. And then now we want to find the fundamental equation of the system. Fundamental equation of the system means a equation which involves certain state variables. So it can be U, it can be T, or it can be the
It is in the
entropy.
form of, okay, ma'am. So it is in the form of PV upon T, fundamental equation.
Yeah. Yes, yes.
Uh, it
I-
it forms in PV upon T in the fundamental equation type.
See, when you write the fundamental equation of state for maybe ideal gas, what do we write? We write it as PV equal to nRT, something like that, right? So
Yes.
that involves state variables like pressure, temperature, volume, correct, and the number of particles and all of that. So similarly, you have a system where the internal energy is specified and it's given as P into V. And then your pressure is also specified, which is given as B into T square, where B is some constant. Now you want to find the fundamental equation of system, meaning a equation which describes how the system will evolve. Okay, so if you are, so that means this equation will include certain state variables which describes the state. So what are state variables? So it can be, so It can be like the pressure, or it can be volume, or it can be uh, maybe the entropy,
Ye-
something like that. Okay.
Yes, it can be SB and S mu and type.
Hmm.
So number, I think we have fundamental equation of type SBN, and so I am getting how to get the number of particle in this equation. So it is necessary to write the in n terms.
No, it's not necessary. Whatever equation you have to define it in terms of that. It's not
Okay.
necessary that it has to be
So
n, like it has to have n.
we can write it is in PVT. Okay.
Yeah, it
S
can
is
be
the
in terms
function
of,
of PVT.
yeah, it can be in terms of PVT.
Okay.
It can be.
Like the Gibbs equation, right?
Hmm?
We can express it in terms of the Gibbs equation.
So gives you mean the gives free energy parameter?
Yes, ma'am.
Yeah, so that is a potential. So gives free energy is a potential which defines the system. So that can be a variable. Okay, but that is not the only you can say. So that describes the state at a particular under particular conditions. But then equation of
No,
state.
I'm saying we can express it in terms of like G is equal to minus uh, DST plus PV. Uh,
Okay, okay,
that
okay.
equation.
So if you do that, then ultimately you have to solve it out to find an equation. So you can start with that. And then, so what happens is that ultimately you get a equation which involves the state variables.
Right.
But keep in mind, these are the values that you have. So this is, you have U, and then you have P. You have to, so, okay, let me just see what you guys think. And so I think because it's already 7:30, I have another question to share. So maybe I'll share the solution, and then we will discuss the solution and see if you have other ideas in understanding the question or addressing the question. Is that okay?
Yes,
Okay.
ma'am.
Yeah. Okay. So see, this is how we are proceeding. See, till this we already know. This is what we have been doing in the last question, right? ds dv at constant uh, internal energy is equal to p by t, and del s del u at constant volume is equal to 1 by t. We know how to get to this, correct?
Yes, ma'am.
Yeah, we did it in the last question, just in the last question. So now what we do is, here our u is already specified, correct? So what we do is p, we can we can write u in terms of this parameter. Is this making sense? So we just replaced P here so as to write U, the internal energy, in terms of temperature. And then we find 1 by T.
Yes, ma'am.
See, because see, we want to find this, so we want to remove all differentials, and finally we have to integrate and get the state variables. So here we know U, we know P, we have temperature, we have volume. So what we do is we find the expression for 1 by T, because we know that 1 by T has a dependence on okay, okay, so 1 by T has a dependence on the internal energy. So this is the expression for 1 by T. You guys are getting it, right? So we find the expression for 1 by T, we find the expression for P by T, and then what we do is we put it here in this expression. So here, if you do that and then if you integrate, you get an expression like that. So here you see that this is a constant, and then it's a function of internal energy, which is a state function. Then you have volume, and so it's a state variable, and then you have S. So this is the fundamental equation which describes how the system is supposed to evolve. Or given these parameters, given the internal energy or the volume, what would be the S or the entropy of the system? So you can start with some other, maybe if you, I don't know, maybe some other value. So here we have taken this, we have tried to find it in terms of S. Now so you were saying in terms of G. So I don't know what is the expression you would get, but then you have to start it from here and then use the available relations that is there to find these values, do the differentials, and then integrate to get the equation. But then what is the optimum choice depends on what are the available things specified in the question. Is that okay? Are you guys there?
Yeah, ma'am.
Yeah, okay, okay. So if you have any doubt regarding this, you can ask me. Is there any problem, guys? Or are you trying to understand certain step?
No, ma'am. It is okay.
Is it okay? So should I proceed?
Yes.
Yeah, okay, fine, fine. Okay, so I was waiting for your responses. That's why. Okay, so this is another question. So here we have the expression for U, and we know this is the initial temperature and the initial pressure. And the system undergoes an isoentropic change so that the pressure is halved. So we know that the final pressure is P naught by 2. So what is the final temperature? So any idea how we should proceed with it?
First, we think isoentropic process. That means ds equal to 0.
That means in the expression for U, S is constant.
Yes.
Correct. So now you have U in terms of V.
And here R is the universal gas constant, ma'am.
Mm-hmm. See, somehow we know that the pressure has become half. We want to see what the temperature will become. So that means we need a relation between temperature and pressure, keeping other things constant. So something like, see, when we do maybe consider this question where you have an adiabatic process and you know the initial pressure and volume and you know the final pressure. How do you find the final volume? So we know that PV to the power gamma, P1 V1 to the power gamma is equal to P2 V2 to the power gamma, right? So is equal to constant. And then we use that relation to find the final temperature. So you have to use a similar kind of concept here where we already know what the pressure has become. We want to find what will be the change in temperature. So somehow we need an expression where we have P and T and they are related by some constant. Any idea how to address the question? Try to use that expression like how internal energy is related to pressure and
I am you yes yes same as I am using internally the function of p and t, and I am getting du equal to the same thing just like previous procedure for dc ds.
ds. Okay. What about others? How are others dealing with the question?
And I then du equal to db du upon dv equal to minus p from the question statement I am getting minus p equal to du upon dv because 3ds isoentropic process. So
I just lost you. Wait, one by one. Tell me one by one. I just lost.
okay, I think I am just only saying.
No, no, it's okay. You can just either try to solve it, or if you say it, like say a little bit, maybe slowly. I'm just losing the track of what you're saying. So you have U, which is in terms of V and S. Should I try sharing the solution and then we can together deal with the question?
And we just differentiate both sides.
Okay. And then?
Um, just a minute.
Okay.
We can use the concept of adiabatic equation we have just PV gamma I T P gamma minus 1 like.
No, see, this is not an adiabatic process. This is
Yes, yes.
isoentropic process. I was just telling that when we solve this kind of questions, suppose the initial pressure and temperature is given, and and the final pressure is given, we want to find the final temperature. So what do?
Yes.
We use a relation where we know that there is some dependence between P and T, and then it's equal to some constant. So if we get something like that, we can write it in terms of all the known quantities and find the unknown, right? So we need to find an expression where we have P and T, and then that is equal to some constant term. So then what we can do is we can just relate it to the initial equal to final, correct? So here, see, you have the expression for U, correct? U is the internal energy. Now use the maybe use the first law. So what does the first law tell us? The same expression, like the first law is like du equal to
D equal to DQ plus PdV.
du equal to so it's like TDS
Sorry, sorry.
minus PD, yeah,
PdV, yes.
minus PDV.
So,
D,
yes, but here from the question TDS goes to 0 because it is isoentropic process.
yeah, that is fine. But
Yes.
we don't need to we don't have to do that here. First write the differentials because we want the expression for temperature and we want the expression for pressure. Correct. So you have entropy and you have internal energy, you have volume in the expression. So just use the expression like del U del S equal to T. Del U del S at constant volume is equal to T. See again here. So initially, I think Anushka had this doubt that we were using an expression where it was at constant volume, and then the question did not specify it's at constant volume. But that relation which comes from the differential is always true. Okay. So del U del S at constant volume is equal to temperature. That is always true.
Yes, ma'am.
Okay. So you have the expression for U which has entropy with and you have V. So find out del U del S at constant volume. That will give you temperature. See this. So well, if you initially just put S equal to constant and then ds equal to 0, so what does del U del S mean? So is it like infinity or something? That's
So,
not correct because we have to first write the expressions. So
so from the expression we get the expression for T and P.
yes, correct. So you have U. You know how to find temperature and pressure for that, right? We have already done this. So this
Okay,
equations.
so yes, so we have a T and P. So we can write initial temperature, initial pressure, and final temperature and final pressure for this.
Yeah, that you will do. But first find the expression for temperature and pressure. You have U. So find du ds. Du ds at constant volume is temperature, correct? That we already know. Do that. See, the state variable is this, na? The state variable, write it in terms of the differential. Okay. So, like you have U. So,
Ma'am,
yes, yes.
ma'am, what I had done was the given equation of u in terms of v. So I just differentiated both sides. So I got du is equal to minus 2a e raised to s by r v raised to minus 3 dv. So I got du in terms of dv, that equation, and then I thought I could put TDS equal to du plus PdV. So
Hmm.
I could replace du in terms of dv with that. So the ultimate equation which I'm getting is TDS equal to the constant minus 2a e raised to s by r into v raised to minus 3 plus p and whole bracket dv.
Yeah, see, here the thing is that when you already consider S as constant and you don't use that differential, you'll miss out on something, right? So
Yeah.
Okay, ma'am. So
how do you find
from
uh,
actually, ma'am, we have t equation. So can we write e to the power s upon r from the peak in terms of p?
in terms of P? Okay, you can write that. You have to
Okay, yes, ma'am.
ultimately you have to have P which has some constant and then maybe volume. See,
Yes.
the thing is that this is your U, right? You know U. So Anushka, see, try this is U. Write it in terms of the differential first. Okay. So what is du? Du is equal to TDS minus PdV. Correct?
Yeah.
So then du ds at constant volume is temperature. Is it matching? Um, so du is equal to, sorry, what am I doing? Just consider it as
I think
equal
I
to.
am approaching to the some answer. We get the TP equation T in terms of P. So T equal to A upon 2R into P. So AP upon 2R. T
A
equal to
T equal to
AP upon 2R.
A P upon 2R. There's something might be
So now we
okay. So let us
actually
do the
first okay, I explain. First we get T and P equation.
yes. So
Then
how do you
then
get it? One second, because I think there's a confusion there as well. So see, this is the expression, right? TDS minus
yes.
PdV. Anushka, see here. So this is the expression, okay? And then right. So you have differentials here as in terms of S and V. So now write it as del U, uh, del U del S into ds, okay? And then plus, maybe I'll just not write, just you can just write, I'm just telling you. So that will be del U del V dV, correct? Is it making sense, Anushka?
Now confused.
Okay, okay. So see, you have a variable that is U. It is written in terms of two variables, volume and entropy. Correct? You want to use this to find temperature and pressure. So how do you do it? You write the differential for U. Write the differential for U. This is the differential. Till then it's correct, right? This you can understand.
Yes, ma'am.
And now, so if you consider U to be a function of, sorry, this just ignore my equal to, this is something. So U to be a function of S and V. Okay. Just a normal differential concept. U to be a function of S and V. So how do you write du? Du equal to del S, del U del S into ds plus del U del V into dv. Correct?
Ah, okay, ma'am. I got it now.
Yes. So now compare this two and try to find temperature and pressure from there.
Okay.
Correct? Abhinam, you are trying the same way, right? You are trying P
Uh,
and T.
yes. And I am getting the final temperature equal to P naught upon 2. It's
P naught
right.
up P naught upon 2 is actually not right. It's maybe some uh, calculation mistake that you have done. So I'll share the solution maybe. and then we'll see where we have gone wrong. Okay. So see, this is the expression for t, and this is the expression for p. Okay, correct.
Yes.
Now what we do is we use these two relations to find this value, so that see, we have to cancel. Here we have v square, here you have v cube. So we have to cancel this two so that we have only constants, and then we get a relation like this.
Okay.
This is the relation that I was talking about. So now you can just use this relation, t naught cube by p naught square is equal to t final cube by p final square. Is this making sense?
Yes, ma'am.
Yeah, okay. I don't know where I was in a meeting. Okay, so for everyone, is this making sense? Is the question clear to you, all of you?
Half of the
Up to
solution is
t.
matching from me, but I think I am mistaking last.
I have find the value of t, but after that I couldn't follow you.
So you found the value of t, and then did you find the value of p? So it's just the differential. See, you have this expression. You do del u del v at constant entropy. Just use this relation. There might be some calculation mistake that some of you are doing.
Yes. Ma'am, the equation is dq upon p square is equal to constant. This is not clear for me.
So you have the
Mr. K.
expression for t, correct? And you have the
Yes.
expression for p. So
Yes. Same equation. Same
a,
solution I have.
yes, yes. So a is constant, s is constant, r is constant. All of them are constant, correct? It's an
Okay.
isoentropic process. So what is variable? Only v is variable.
Yes.
So here you have v square, 1 by v square. Here you have v cube, 1 by v cube. So how do you cancel them? So if you multiply t by 3, like if you uh, find the cube of temperature, then it will be 1 by v to the power 6. And now if you do square of p, it will also be 1 by v to the power 6.
Yes.
And then if you divide, what happens? This two get cancelled.
Okay.
So what you have is just a constant term.
Yes.
So that's how you get this expression.
I yes, ma'am. The same answer is the constant term is a upon 2r. That's okay. Okay. So okay, I understand.
Okay, okay.
Okay.
Can others understand? Jamuna, can you understand?
Yes, ma'am. Yes, ma'am.
Yeah, okay. So Anushka and everyone, Ayub, everybody, is it clear to all of you?
Okay,
Yes,
ma'am.
ma'am. I got the answer.
Yeah, okay, very good. So I think it's already time, and this was my last slide. So, okay, so we finished just in time. Okay, so thank you. Uh, I hope
Thank
you
you, ma'am.
could. Yeah, thank
Thank you,
you.
ma'am.
Yeah, I
Thank
hope
you,
you
ma'am.
could
Thank you.
understand this. Maybe we'll again meet on next Monday with some more
Yes.
questions. Okay.
Okay,
Okay,
ma'am.
madam.
Thank you.
Ma'am, can you please share the recording of this meeting?
Yes. So it will be uploaded in YouTube, and that the link will be there, I guess. Okay. So and we'll also share the PPT of the slides for your reference. Okay.
Okay, ma'am.
मैडम एक पहले हेलो मैम
Yes.
একটু ওই ম্যাটারটা পেলে ভালো হতো, পিপিটি।
হ্যাঁ, হ্যাঁ, হ্যাঁ। পাঠাবো। ওটা আপলোড করা হবে। So, uh, uh, so it turns out we are Bengalis. Okay. So, so we'll upload the recording. It will be in YouTube. So we'll upload that, and we'll also upload the this PPT. I'll make a PDF out of that, and maybe I'll share it in the drive. Okay.
ওকে ম্যাডাম।
Okay, ma'am.
Okay. Okay.
Will we receive the link by email, or will we have to check the NPTEL website for that?
I guess it will be uploaded in some in a sheet, in a Google sheet. So you'll get the link there. There's a Google sheet, I guess, with my name. Isn't it shared with all of you guys? It's not shared.
No, ma'am. There was a session yesterday, but we have not yet received its the PPTs and the recordings too. So,
Okay, okay. Even I am like it's the first session, so I need to clarify certain things. But what we have been given is we have a Google Sheet where we can share the link and the drive link as well. So once I upload these things in YouTube and in the drive, maybe I'll contact. If it is not shared to you, I'll contact the NPTEL authorities and see how this is to be done. Okay.
okay, ma'am.
Okay, okay. Okay, nice meeting you, all of you, and we'll meet
গুড
again
নাইট।
next time. Okay, yeah, bye, bye.
Bye, ma'am. Thank you, ma'am.
Thank you,
Bye,
thank
ma'am.
you.
Thank you.
Bye, bye.